choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Get my feet up. Okay, I'm on.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 33 minutes past the hour. Liftoff on Apollo 11.
Listen, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 112 of the Space Rocket History Podcast. And now, Apollo Headquarters. Once all the vehicles in the Apollo stack had been decided on, those already being developed would have to be changed to fit the new concept of Apollo. Most immediately affected was North American's command module. The shape of this craft, a conical pyramid much like the bell-shaped Mercury, had been set very early. But this blunt-body vehicle was designed only for Earth orbital and circumlunar flight. As you may recall, there was also some thought given to attaching propulsion stages to make a direct flight, with the command module landing on the lunar surface. But, of course, that plan was abandoned once the Lunar Orbit Rendezvous mode was selected. But Lunar Orbit Rendezvous mode forced the inclusion of some means for docking the command module with the lunar module and transferring two astronauts into the lander for the trip down to the moon. So now, command module development had to take two routes. Configuration systems and subsystems had to be qualified, and astronauts had to be trained in Apollo operations, which could be done in Earth orbit flight. It was therefore unnecessary to make any major changes on what came to be called the Block 1 spacecraft. But the time limit set by President Kennedy did not permit waiting for the first Block 1 version of the spacecraft to be completed and tested before starting on an advanced model, Block 2 version, that could perform the new docking operation. Both the Block 1 and Block 2 spacecrafts had many components in common, but development had been infinitely more complicated. In fact, Deputy Administrator Hugh Dryden called the Apollo program, quote, the largest, most complex research and development effort ever undertaken, end quote. All three of NASA's manned spaceflight centers, Huntsville, Cape Canaveral, and Houston, had their hands full during 1963 and 64. Marshall was wrestling with the mammoth Saturn V development program. The biggest concern was the propulsion system. The F-1 and the J-2 engines could not be simply picked off the shelf and fitted with the appropriate oxidizer and fuel tanks. There were difficult days ahead before the contractor Rocketdyne succeeded in developing and qualifying these engines so they could be trusted to boost astronauts toward the moon. At the Cape, the Launch Operations Center was doing some educated guessing about the flight preparation facilities needed for the spacecraft and the launch vehicles. And the Manned Spacecraft Center in Houston was working on three major problems: flying the last Project Mercury spacecraft, that was Mercury Atlas 9, and getting spacecraft development underway in both Project Gemini and Project Apollo. Fortunately, Apollo, because of its modular configuration, had no immediate need for day-to-day coordination among the centers at Marshall, the Cape, or Houston. This freed the program offices to work independently in solving their more pressing problems. But the Apollo program needed to be centrally managed, technically as well as administratively. and it would have to be armed with a large force to accomplish this. This meant that NASA headquarters had to become more technically oriented and participate more in the daily activities of the program. Which brings us to the new role headquarters was going to have to fill for the Apollo program. Shortly after Brainerd Holmes joined NASA headquarters as its first director of manned spaceflight, he and Administrator James Webb contracted with General Electric for studies on reliability and quality assurance, analysis and integration of the complete Apollo vehicle, including spacecraft and booster, and procurement and operations of ground equipment to check out and certify the vehicles for flight. To fulfill this task, General Electric engineers had to immerse themselves in the day-to-day activities of the spaceflight centers. No one in the field complained about GE's role in the reliability, quality assurance, and checkout functions, since the space centers wanted all the help they could get in these areas. But the suggestion that a contractor should tell government employees how to put their vehicles together to fly a mission was resisted. Edward S. Miller of General Electric said, quote, "The contractor role in Houston was not very firm. Frankly, they didn't want us. There were two things against us down there. Number one, it was a headquarters contract, and it was declared that the space centers shall use GE for certain things. And number two, they considered us, meaning GE, to be headquarters spies." End quote. For some time after the contract was awarded, just exactly what General Electric was supposed to do was not clear. Back in February of 1962, General Electric engineers began holding monthly review meetings, but they met with little success in selling their plans for spacecraft and launch vehicle integration. After several of these gatherings, contractor officials complained that NASA people did not understand the role of GE. Nevertheless, in August of '62, General Electric transferred 15 of its engineers to Houston. To get the contractor into Huntsville operations, the manager of the headquarters office for integration and checkout accompanied several General Electric employees to Marshall to explain to the center and the Saturn contract officials General Electric's role in the Apollo program. Of course, the contractors, Boeing and Chrysler, did not want any unannounced visits by General Electric engineers, especially since the two principal Saturn contractors could not foresee any way in which General Electric could be of assistance to them. So, Marshall and the contractors were assured that all visits would be arranged in advance. Now, General Electric's other major task of designing, setting up, and operating ground equipment to check out the flight vehicles was accepted at the field centers. In fact, Manned Spacecraft and Launch Operations Center representatives said they were satisfied with General Electric's work in this area, and Marshall actually asked for more help. Even here, however, there were some reservations about turning General Electric loose. The Apollo manager in Houston, for example, emphatically warned GE to do nothing unless it had a work order approved by the Apollo Spacecraft Project Office. Eventually, the General Electric contract called for almost 1,000 people, more than half of them stationed at Daytona Beach near the Cape launch site, where they designed and assembled the ground checkout equipment needed to test the space vehicles for flight safety. The remainder went to the 3 NASA centers and to contractor plants, helping to ensure the receipt of good quality hardware and performing specialized studies when they had a work order. Administrator Webb set up the General Electric contract to provide NASA headquarters with the technical specialist to watch over and participate in Apollo's far-flung development activities in both government and contractor establishments. He also wanted a bevy of engineering systems specialists near at hand to assist Brainerd Holmes in making technical decisions. Webb asked Frederick R. Capel, president of AT&T, to form a group to provide this talent for Apollo. Bellcom Incorporated, the new AT&T division, began operating alongside Holmes's NASA headquarters manned spaceflight engineers in March of 1962. Holmes immediately directed the contract engineers to work with Joseph Shea, first on the study of the mode issue and then on the defense of NASA's mode decision. Once the mode studies were completed, Shea decided that Bellcom engineers should dip into mission planning and produce some reference trajectories. By reference trajectories, I mean a careful analysis of everything involved in flying the space vehicles from the Earth to the Moon and back. But when Shea took his newly formed Apollo Trajectory Working Group to a meeting in Texas, he met with stern resistance. John P. Mayer, speaking for mission planners in Houston, said that his group had been doing this kind of work for the past 2 years. Mayer told Shea bluntly that interjecting Bellcom into mission planning was just one more attempt on the part of headquarters to move into operational areas that properly belong to the centers. Shea explained that Bellcom would be a supporting group and would not try to second-guess the centers. Many in Houston perceived Bellcom representatives who attended most of the subsequent trajectory meetings as being just like General Electric, headquarters spies. What continued to upset Mayer and his colleagues in trajectory analysis was that Bellcom, not always on the scene, simply could not keep up with the latest operations data, mission rules, and guidelines. As a result, Bellcom sometimes gave headquarters out-of-date information, and the field centers had to spend much needed time in correcting misconceptions. Nevertheless, Bellcom, which never employed more than 200 people, did produce some useful evaluations on almost every aspect of Apollo throughout the decade. These engineers were among the first to push for the pinpoint lunar landings that were so successfully carried out after the first landing mission. Along with the mounting strength in contractor personnel, the Manned Spaceflight Office in Washington, which had only a handful of people in Mercury's early days, also increased in number. By February 1963, Holmes had a 400-person force, presided over by himself and his deputies, George Low and Joseph Shea. Low managed space medicine, launch vehicles, and office operations. Shea concentrated on engineering matters. Much of the energy of the headquarters office and its contractors during 1963 was devoted to drafting an Apollo Systems specification book. The goal of this document was to lay out the objectives, to define the technical approach for implementing these objectives, and to establish performance requirements. The task was difficult because many systems, especially those in the Lunar Module and the Advanced Block II Command Module, simply had not been studied enough in detail for anyone to state positively what was expected. Numerous pages were stamped "to be determined," but there was some clarification of policy for Apollo. Up until this time, the main objective had been expressed only as landing a man on the moon and returning him safely before the end of the decade. The specification book intimated for the first time that exploration of the moon would not be limited to a single mission. A number of interesting specifications in the manual remained valid throughout the program. For example, all parts of the spacecraft would be designed to minimize the fire hazards inherent in the use of pure oxygen atmosphere that North American had been directed to incorporate in the command module in August of '62. North American was also instructed to design the command module so a single crew member could return the craft safely to Earth from any point in the mission. And the service module would provide all spacecraft propulsion and reaction control needs, including attitude changes in pitch, roll, and yaw from lunar transfer until it was jettisoned just before the spacecraft re-entered the Earth's atmosphere. Now, hand in hand with definition of the system specifications were the systems review meetings sponsored by the Office of Manned Spaceflight. The meetings had a twofold purpose. One, to gather information for the specifications book, and two, to make sure that centers coordinated all activities in Apollo's complex development. At the first of these meetings, Shea found a gap in this coordination. Marshall was having trouble with F-1 engine combustion instability. Yet, an offer to help from Lewis Research Center, NASA's leading propulsion organization, had been ignored. Other instances of this lack of cooperation may have occurred, but the three manned spaceflight centers had moved closer together, partially to defend the mode choice, and partially to stave off the intrusion of General Electric into vehicle integration. On top of that, each center had a great many questions that needed to be answered by the other field elements, and they were working together on policies and mission rules that became the foundation for the lunar landing program. At a mission planning panel meeting, some of these ground rules emerged. 2 crewmen would land on the moon, and 1 man would remain with the command module in lunar orbit. The lunar lander could stay on the moon from 21 to 48 hours. Launch from the Earth would take place in daylight to simplify recovery operations in the event of an abort. Launch to the moon from Earth orbit would begin within 4.5 hours because of the boil-off characteristics of liquid hydrogen in the S-4B stage, and the first lunar mission would be only a loop around the moon and return, since too little was known about the start and restart capabilities of the service module engine. Most of these committees, and there were many of them, took turns meeting at Houston, Huntsville, and Canaveral. By May 1963, the panels were so numerous that Holmes realized something had to be done to keep track of them. He told Shea to form a panel review board as one more headquarters tool for managing Apollo. Shea convened the first meeting of the board in August of 1963 at the Cape, and representatives of each panel summarized their past activities. The next item on the agenda was a session on standardizing the interface control documents and the selection of Marshall as the repository for this documentation, to make sure it would be available for reference by the participating organizations. These periodic board meetings, besides keeping the Office of Manned Spaceflight closer to the mainstream center activities, gave the specialists a chance to learn what their colleagues were doing and an opportunity to oversee progress, cost, and schedules. Areas that might delay Apollo were discovered more quickly and dealt with more rapidly. Occasionally, NASA headquarters had to step in to arbitrate among the sinners. At one time, telecommunications threatened to become a formidable issue in Apollo, with Houston, Goddard, and the Jet Propulsion Laboratory vying for control of the tracking network. The Earth-circling band of stations, about 12.5 used in Mercury, were not equipped for the deep space communications required for Apollo. But by 1963, a capability was developing in the unmanned spacecraft programs that promised to be suitable. The Jet Propulsion Laboratory intended to build 2 sets of 26-meter dish antennas with 2 antennas at each of these 3 sites: Goldstone, California, near Canberra, Australia, and near Madrid, Spain. That would provide continuous communication coverage of the moon. One set would be equipped with the more advanced unified S-band system for controlling, tracking, and acquiring data from unmanned spacecraft, similar to Mariner and Surveyor, currently in deep space. This system consolidated the functions of the many transmitters and receivers characteristic of Mercury into one by tying the signals for tracking, telemetry, voice, television, and command into a single radio carrier. The Mercury tracking stations with 9-meter dishes and the new S-band radar would communicate with the Apollo spacecraft in Earth orbital flight. Once the vehicle had traveled 16,000 kilometers into space, the 26-meter antennas, spaced equidistantly at 120 degrees longitude around the Earth, so one of the 3 always faced the moon, would take over. Later, the Jet Propulsion Laboratory was to build a 64-meter antenna at Goldstone that would give Apollo clearer communications, especially in television reception. The laboratory wanted to construct 2 of these stations, but the costs were too high. The British government, however, had a radar station with a 64-meter antenna at Sydney, Australia, that could be used. Although some of the finer points on communications and control were haggled over for the next 15 months, in March 1963, NASA Associate Administrator Robert Siemens settled the basic issue of who was in charge and when. He assigned Goddard as the technical operator of the Manned Spaceflight Network. During Apollo missions, the Manned Spacecraft Center would assume operational control. The Jet Propulsion Laboratory would be in charge of all unmanned mission communications, turning its facility over to the other centers during manned flights. By the end of 1964, headquarters had the communications and tracking requirements and assignments for Apollo pretty well in hand. Other NASA headquarters offices, besides manned spaceflight, assumed lead roles for Apollo, especially in the area of scientific interest. Because of the complex engineering task, no one really expected that science would do more than ride piggyback. Just about the only scientific concern the Houston Center displayed was in the composition of the lunar surface soil, which would affect the design of the landing gear. Director Robert Gilruth sent a representative to a meeting of NASA's Space Science Steering Committee to ask for help on the soil question and to remind the members that whatever scientific equipment they might develop would have to be adaptable to the lunar spacecraft. But scientists also could be of immediate help in determining where to land on the moon and what the astronauts could do after they got there. Shortly after President Kennedy had issued the Lunar Landing Challenge, Homer Newell of the Headquarters Science Office asked Harold C. Urey of the University of California at San Diego to suggest the best scientific sites for lunar landings. Urey told Newell of the 5 kinds of lunar terrain of particular scientific interest. First, the high latitudes, to check for possible temperature differences from equatorial areas. Second was Maria, also known as the dark regions of the moon, to try to determine the depths of holes where great collisions had taken place, and on a second landing to discover the composition of the material in such places as the Sea of Tranquility. Third, inside a large crater, to look at an area, probably Alphanus, where observers had seen gases rising from the interior. Fourth, near a great rille or wrinkle in the Maria, to attempt to find out what had caused it. It had been suggested that water rising from the interior had cracked the surface as it dried. And fifth, in a mountainous area to observe crater walls. In 1962, a 2-month summer study conference in Iowa was co-sponsored by NASA and the National Academy of Sciences. The results of deliberation were published under the title of A Review of Space Research. The study outlined the broad objectives of a science program for Apollo. Conclusions were that the most important scientific tasks foreseeable for manned lunar exploration were educated observations of natural phenomena, the collection of representative samples of surface material, and the installation on the moon of certain scientific monitoring instruments. Late in 1963 and early 1964, NASA headquarters established science planning teams. The teams were assigned these responsibilities. First, recommend investigations of the lunar surface. Second, provide designs for prototype long-life geophysical instruments. Third, determine requirements for astronaut training. Fourth, building of a receiving laboratory for handling return samples. And fifth, provide plans for the reduction and interpretation of geological, geophysical, solar, astrophysical, and other scientific data. Although the work of these teams was barely visible to outside scientists, NASA had some of the best specialists in the country helping to formulate its general objectives on the lunar science program. 5 fundamental areas emerged as having the greatest potential. First, studies of the lunar lithosphere, the solid moon itself, its chemical and physical constitution, and the implications this should have for its origin in history. Second, investigations of the gravitational and magnetic fields and forces around the moon, including experiments for the possible detection of gravitational waves. Third, considerations of particles like solar protons and cosmic radiation, together with their effect on the lunar gravitational field and magnetosphere. Fourth, establishment of astronomical observatories on the moon. And fifth, studies of proto-organic matter, including the possibilities for exobiology. Realistically, everyone realized that the first manned visit to the lunar surface, limited to no more than 24 hours, would hardly satisfy the desires of most scientists. With proper planning, however, a bonanza of scientific results could be gleaned even from that first landing. In June 1964, the Mineralogy and the Petrology planning team underscored these hopes by drawing an analogy between the lunar voyage and another historic event. Here is the excerpt. Quote, "Sometime before the year 1492, A group of workmen were standing in a shipyard looking at a half-constructed craft. One of them said, "It won't float." Another said, "If the sea monsters don't get it first, it will fall off the edge." A third, more reflective than the others, said, "What did they want to go for anyway?" The Apollo project is primarily a glorious adventure in which man will, for the first time, tread upon the surface of another celestial body. It will be a magnificent feat and a milestone in the history of the human race. No other purpose or justification is necessary. Important scientific knowledge will result from the landing. First, among the scientific objectives of the Apollo mission will be the return of samples of the lunar surface materials. The study of such samples will tell us of the thermodynamic conditions under which they were formed, whether the moon is a differentiated body or not, and perhaps whether it was captured by the Earth or was formed from it in the distant past." End quote. Most of the work of NASA headquarters on behalf of the scientific aims of Apollo by the end of 1964 had little impact on the organizations and contractors developing the program. All that the builders needed to know was how much space to allow and a general idea of the future plans. When the time came to fly the missions, however, the planners, astronauts, and flight preparations technicians would have to pay more attention. The outline of what Apollo could contribute to science had been sketched. The details would be filled in later. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.